Okay, next topic is lighting and this Phong reflectance model, which is a good amen. A little bit of background first before I get onto the Phong reflectance model. It's what kind of some terms about lighting. Illumination, local illumination. So local illumination is computer graphics term. It doesn't really have any equivalent in the physical reality. It's just a massive simplification we do to be able to model any kind of lighting situation. And I'll get back to how simplified it is, but right now I'm just going to describe a few terms in this, a few names for stuff when we do lighting calculations. So we have a surface and we have a light source, and there is a camera or a viewer, an eye I'm going to draw, that looks at the surface. So let's assume that at the moment we are considering this one point on the surface. It's like the graphics hardware is now rendering this particular point on the surface and wants to figure out what color it should be based on the lighting situation. So we define a few vectors. From the point we define a vector that goes toward the light source, that tells us from this point where is the light source, in what direction is the light source. And another vector that points toward the viewer. And we call the light vector L, and that's a capital L because it's difficult to see a lowercase l, and it's the same in the book. So we always use a capital L for this vector. And the view vector, we call that V, and some little arrows above them so we can see their vectors. Okay. So we talk of local illumination. That means that when we are calculating the light at this specific point, we only consider the geometry at this point. We do not consider any other geometry in the scene. You know, in the real world, there's a lot of light bouncing around. So if we want to calculate the color value, the light value of somewhere we're looking at, then we actually have to consider how the whole room looks. Because if the room were a different shape, then the specific spot would also be maybe a different light value. But that's global illumination. That's something else. So the simplification is we only consider this one point, and we don't care about the rest of the geometry. And yeah, here I call it the reflectance point. This word reflectance is sort of the general term that we use when light is bounced off a surface and hits the viewer. So this specific point, very small point. Actually, it's infinitely small, of course. Another property which is important, and that's actually why it's simpler to look at it this way, is that at this point we can define something called a normal vector, like this. So there will be a 90-degree angle from the surface to the normal vector. Now this is a 2D situation we're looking at from the side. It's like 2D, and also the surface is completely straight. But again, because we're only looking at an infinitely small portion of the surface, we can always consider it to be completely flat in some direction. And actually, the normal vector, the vector that points at a perpendicular angle from the surface, that actually defines the slope of the surface in 3D space. So we don't need any other information than just a normal vector, then we know the orientation of the surface at this point. That's why normal vectors are very important when dealing with lighting. And We'll call this normal vector n, lowercase n. The final thing I just want to put some terms on is the light source properties. We say lowercase I, that is the intensity of the light, how strong it's shining, and a C, uppercase C, that is the color of the light. They are distinguished in the book. It's two separate things. So that is some properties of the light source. The light source has other properties that could be important as well, but these are always the same, the intensity and the color, I and C. Okay, so a little more about this simplification of local illumination, what it means. In computer graphics we also work with another term called global illumination, and that's the global illumination is what is happening in real life, in real physics. I have a picture here that can be used to illustrate it. This one. I think this is a ray traced image, something like that. But it's a good example of why the simplification is actually not that good. Yeah, so oops. So again, if we consider just a single point, maybe a point on the floor, so we have maybe some light that comes from the windows and hits the floor here, and then gets bounced off the floor. So the light is, the reason we can see the floor is that some of the light that comes from the window and hits the floor actually bounces off toward the camera. But also this is a diffuse surface, so it's actually bouncing in all kinds of directions. So we have, at this point, this one beam of light actually becomes transformed into a lot of little beams of light that go in all different directions. The amount of light hitting any surface depends on entire scene geometry. What we're seeing here is that when the floor is mainly lit from the window, but it's actually also lit from indirect reflections from the back wall, or maybe even the furniture. So if we were to change the color of the back wall, then the floor would also look different to us. It would have slightly different color. Actually, some of these areas are almost entirely lit only by indirect light, like up here, for instance. There's no direct light from the windows hitting that wall, but we can still see it. It's not completely black, and that's because light is bounced off the floor and off the walls, and then hits this wall. So indirect light. So if we could do something like this with the graphics hardware, which increasingly can, but normal graphics hardware doesn't do this per se. If we could that, then we could have much more realistic scenes like this one, with much more realistic lighting. But the problem is that it's too expensive, computationally expensive to do. So you want just simulating just one beam of light, then becomes a lot of beams, and each of those maybe hits another surface, and then each of those becomes a lot of other beams. So the algorithm to calculate the light is really complex, has high complexity. Expensive to simulate. Yeah, and that's actually also, as I said in the beginning, I think it's seen is ray traced, which is one technique to actually simulate like global illumination. And it's normally not, ray tracing rarely happens in real time. It often takes a long time to just render one image like this, because what you do in ray tracing is actually that you trace the lighting backwards from the points where we see them and backwards to see if any beam of light actually comes from a light source or not. And again, that's very expensive, because every time you hit a surface, then just one line of light has to be traced in a large number of lines. So this is not what we do at the moment, although a lot of graphics programming in general and a lot of lighting graphics programming is about simulating this in different ways to have less expensive ways of doing something that looks similar. Okay, but let's go back to this situation here, local illumination. We only consider the geometry at the specific point that we're looking at and nothing else. That's what we want to do now. As I said, I put these two properties that are general for light sources, how strong the light is and maybe what color it is. Another property that we assign to the light is what way the light source emits light. And we use a few simplifications from a sort of a real-world light source. All of these simplifications that we'll be working with, they all simplify light sources to the point where the light source is like a singular point in space. And most real physical light sources, or all physical light sources, are not like that. They occupy areas. But for simplicity of calculation, we assume that the light source comes from a single point. And there are three different kinds of model for a light source that we use normally in graphics programming. The first one is called a directional light. So I'm just going to illustrate that with a bunch of arrows. A directional light is very similar to the real world phenomenon, sunlight, light that comes from the sun. So it's like an infinitely distant light source. So the sun is not infinitely distant, but almost. And that means that all the light beams that comes from the sun on a sunny day, they're all parallel. They all shine in the same direction. So if you hold up an object, then the shadow has the same size as the object, because all the light beams are parallel. This is called a directional light. And infinitely distant like the sun. The second type is called a point light, sometimes also referred to as an omni-light, but that's an old expression. So imagine there is a single point in space from which light is emitted in all directions. So it can, the light source has a position in space. It's not infinitely distant. It is somewhere in the scene that we're rendering. And you have equal amounts of energy radiating in all directions from the light. Point light is the most normal expression for that. Omni light source. Omni is omnidirectional. It means that every direction. Light is emanated in all directions. And the third type is specialization of point light, spotlight we call that. It works much the same as a spotlight, but light is constrained to certain directions, so it's attenuated down to 0 away from this direction. You can draw it like this. You can also draw like a cone. So the cone sort of represents where the light is shining. So like this maybe, and then, oops, something like this. Spotlight. Cone-shaped beam. And then we can also work with light sources that are not point lights. So I'm just going to put like a general version of those on the slide. So this is kind of like a skylight or something, like a window in the roof where light shines from. And the main difference, of course, is that it's not a single point. It's like a whole area that emits light. You can imagine many different types of light sources that have this property. Light sources that are not single points. Three, isn't it? I'm going to do just one more slide and then we have a quiz. I'll just say a little more about the first type, which is directional light sources. We can illustrate. I use this illustration, this shining light bulb, to just denote any kind of light source. And we could put this, although we cannot put it in the scene because the directional light is infinitely distant. So the position of the light, we call that P. That is infinitely distant, so we don't use it in the calculation. Infinitely distant. Let's draw a few beams here. So everywhere in space the right direction is the same. We normally draw a vector in the opposite direction, and that's because when you saw this other slide, so you like to draw this this L vector. That's actually a vector that goes from the reflectance point toward the light source. So in case of a directional light source, the light source is infinitely distant, so at all points in the scene, this L vector will be the same vector. But it would be, when I draw these, it's like the direction light is flowing from the light source. The L vector, of course, will be in the opposite direction. And that's just a technicality, but important. Oops. So we draw there. And the black ones are light beams, not the light vector. The final point is that everywhere in the scene the intensity from this light will be the same. So other light sources have what we call attenuation. It's like the further we get from the light source, the weaker it is, the less energy it has. But the directional light source does not have this, it has the same energy wherever we are in the scene. So no attenuation. Okay, like this point. So maybe put a little dot here or something. This point, they're all the same. Okay. Please do the poll.